London-based technology startup has become the best-selling paid app on Google Play for 2 years in a row and a #1 hit in 58 countries. Its features have appeared on more than 200 million devices so far. It has raised more than 20 million to date from angel investors and VCs, including Accel Partners, Index Ventures, and Octopus Investments. Please welcome to the stage co-founder and CTO of Swiftkey, Ben MEDLOCK.
Great. Thanks, everybody. Really happy to be here in this beautiful city. I was just chatting to Plaman. He was saying, where else can you take a boat to get to a conference? Very, very cool. Okay, so I'm going to talk about using big data to build the world's smartest keyboard. But actually, quite a lot of what I'm going to do today is talk about some background to the field that we work in. And essentially, I'm going to talk about, take you on a very quick journey through the background to the field of artificial intelligence. Because there's a big crossover between AI and big data. Big data is essentially what allows AI to happen in the real world. Now, back in the 50s and 60s, when the phrase artificial intelligence was coined, people were extremely optimistic. They believed that within 20 or 30 years, we'd have robots that were doing the ironing or helping out around the house, driving our cars. Well, perhaps we're kind of close on the cars, but the reality is we've tended to be overly optimistic about what AI can deliver. So I'm going to talk about how AI has evolved and how companies like Swiftkey are using AI today to solve some difficult problems. So I'm going to start by posing a question, which I think is one of, if not the most fascinating questions that we can ask as human beings. And that's, how do we think? And if you're an engineer, then the follow-up question to that is, how can we model how we think? And the development of artificial intelligence is essentially people asking this question and then trying to build machines that answer the question in reality. Now, the human brain is the most incredible organism. As far as we know, it's the most complex organism in the known universe. And the density of connections within the human brain is still thousands of times greater than our most sophisticated supercomputers. So it's a big challenge. The question is, how do we go about attacking this challenge? How can we model how we think? In order to answer this question, we have to look at how we think. And I want to outline the fact that there are really two processes at work in the human brain. And we tend to divide these into the conscious mind and the subconscious mind. And human thought is a complex blend of these two types of processes. Now, when we think about software engineering and the drive to build an artificial intelligence, in the past, we very much focused on models of conscious thought. And we've kind of left the study of the subconscious to people like Freud up here on the slide. So how well does that work? So if we go back to John von Neumann here, who's the father of modern computing, he came up with the architecture that basically every current computer is based upon. And I want to pick out three elements of that architecture. First off, it's logical. So computers are built from the ground up based on logic gates implemented in transistors. It's also sequential. So yes, we have parallel computers, but essentially parallel is not at the heart of our architecture. One thing happens after another. Instructions are processed through a CPU in order. And then finally, it's debuggable. So this is very important. You can stop a computer at any time. You can trace the exact sequence of instructions that's got you to where you are. And that means that it's possible to evolve the system. It's possible for us to understand. So that's the architecture that models conscious thought. That's how we think. We do one thing after another, and it's all relatively logical. The problem is that models of conscious thought actually don't work well for AI. So the systems that were built around this model, they're just way too fragile, way too frail to tackle the complexity of the real world. So a lot of the enthusiasm around AI in the early days was based on the fact that we thought by building these models of conscious thought based on traditional computing architecture that we could build AI, but in fact we can't. So what about subconscious thought? Now obviously by definition, as engineers and as scientists, we have much less access to subconscious thought because by definition we're not aware of it. But what are the key foundations of subconscious thought? Well, first of all, abstraction. If you start at the level of individual neurons, and then you work your way up to the kind of tasks that we can perform as human beings, there must be multiple layers of abstraction. Second thing is uncertainty, and this is really important. This is one of the things I want you to take away from the talk today. So the real world is absolutely saturated with uncertainty. So almost no problem that you encounter in your life are you able to solve with complete certainty. And just the very basic problems, just walking up the steps, for instance, or getting into your car and driving to work. And so in order to deal with uncertainty, you have to make inferences. You have to guess, essentially. And I'm not talking about conscious guessing. I'm talking about the fact that your subconscious mind is all the time making guesses about the world. This is an example that I like to give. So if somebody at the back of the auditorium throws a ball at me and asks me to catch it, how is my brain going to solve this problem? Well, it's actually a really difficult problem. And what the brain doesn't do is to compute the trajectory of the ball at the point that it's thrown and then make sure that I'm in the right place so I can just catch it. What it does is it keeps refining hypotheses about this problem. So the moment someone throws the ball at me, I probably know that it's heading in this direction, but I don't really know much more than that. As the ball gets closer, I refine that hypothesis. So then perhaps I know that it's going to land within a space of maybe a meter or two on the stage. And as it gets closer and closer, I continually refine that hypothesis right up to the point where I can put my hands out and catch the ball. And this is how the subconscious mind works. It deals with the fact that at the start of a problem, it might be almost entirely uncertain about how to solve it. But it keeps refining, keeps iterating, keeps cycling until it gets to a state where it's certain about how to solve. So now I want to think about how you do AI by using models of subconscious thought, not conscious thought. And I'm going to start with an area of mathematics called probability theory. Probability theory is a phenomenal tool for modeling uncertainty. So we don't know what's going to happen, but we know with some probability that a particular outcome is going to occur. So again, taking the example of the ball, at the point the ball is thrown towards me, with some probability, my brain is essentially working out that it's going to land somewhere near the stage. And some of the guys who were absolutely key in developing the system of probability theory, this is the Reverend Thomas Bayes. And this equation here is called Bayes' theorem, and it's proven to be incredibly useful in so many different areas. And in almost every application of AI, you will find Bayes' theorem somewhere at the heart of it. And this is Thomas Boole, who was, George Boole, not Thomas, who was one of the absolute fathers of probability theory, applying the system of using these equations to understand financial markets. So these guys are really at the heart of modern AI. Now, we've taken some deeply mathematical fields, and this is where the progress in modern AI has come from. So we take statistics, the analysis of huge volumes of data, And that analysis helps us to implement the laws of probability theory that sit behind our modern approaches to AI. And I want to talk about machine learning as well. So machine learning, you may have heard of, it's essentially a field that starts with data, and almost always starts with big data in one description or another, builds a model from that, and then from that model makes inferences, makes guesses about the world. So if you use Google Search or any of the other Google services, you'll find that machine learning is behind them. And my particular background is in the area of applying these models of machine learning to a field called natural language processing, which is essentially trying to deal with the fact that human language is by definition uncertain, and we need AI to be able to understand language. So when I start talking to you, your brain doesn't wait till a sentence is finished to work out what I'm trying to say. It's constantly guessing, it's constantly predicting. I want to spend a few minutes talking about a case study, which is my company, Swiftkey, and how we are applying these modern concepts around AI to a problem that we're all very aware of, which is how do we type on our smartphones and tablets. So traditional typing is a mechanical problem. Building a typewriter is a mechanical problem. And it doesn't require uncertainty. You press a character and then it appears on the screen or the page, and that's fine. In the modern world, when we're typing on smartphones, typing on glass, we're now dealing with a problem that has inherent uncertainty. So when the user types on a particular area of the screen, we don't know whether they actually meant that character or not. And this then makes it an artificial intelligence problem. We need to take the evidence that we get from the taps on the touchscreen and turn that into language. So if any of you have ever had an autocorrect fail, you'll know when this goes wrong. So how do we solve this problem? Well, we actually go back to probability theory. These are our keyboards, this is the product, essentially, that has the software behind it. So we start with maths, we start with probability theory, and say, how is it possible to capture, using the laws of probability theory, what it means to type? So just very quickly here, in black, you have the probability of a sequence of language given the evidence and the model. And don't worry, I'm not going to go into any more mathematics, but what I want to show you is that from this central equation comes different areas that we're able to analyze. And at the bottom here, the features of the keyboard actually come out of the mathematics. So you don't start by building a set of features, you start with this central equation of probability theory. And the idea is that if we can make this equation more and more accurate using data that we gather, then we know we're doing a pretty good job of correcting your typing or predicting the next word that you're most likely to say. Now, the thing about machine learning is that you have to get a lot of data to make it work. So for Swiftkey, in order to build our smart keyboard, we used the European grid, which was originally put together to analyze data from the Large Hadron Collider, which is why I show you the picture here. And we scraped all of the publicly available text off the internet. And we put that, well over 1 trillion words in different languages into our machine learning algorithms. And what we do is to take this huge corpus of data. But the thing about effective AI is that it has to be personal as well. So it has to understand the way that an individual goes about solving their problems. In this case, it has to understand the way that an individual uses language. So we take input from the language that you have created in the past, and we bring these two models together into this smart predictive keyboard that is very good at guessing what it is you're most likely to say next, and very good at correcting the typing mistakes that you make. Now, the other side of this is that we have to be really smart about analyzing the way you tap on the touchscreen phone. So our technology takes the machine learning about the language, and it also takes learning about the way that you as an individual type. So I'm going to show you how this heat map changes. It's representing the probabilities of where you're going to tap on the keys. See how it changes for different users. So we're taking these things together and turning them into the world's smartest keyboard. And this is just some of the numbers. So we've had over 6 trillion characters entered using this smart software. And now it's embedded on more than 200 million devices. And 1.5 trillion character keystrokes saved. And I think that equates to something like 10,000 years of typing time. So that's it. Thank you very much. Please do try out the software if you get a chance. It's called Swiftkey. And I hope you have a fantastic conference.